The truth about wormholes: Einstein's bridge could rewrite time itself.
Wormholes are often imagined as fantastic cosmic shortcuts, tunnels connecting distant points in space or even different moments in time, allowing incredible journeys through the universe.
This popular image, however, stems from a misunderstanding of the original work of two great physicists, Albert Einstein and Nathan Rosen. In 1935, they weren't dreaming of interstellar routes. At the time, they were trying to understand how particles behaved under conditions of extreme gravity and proposed the concept of a bridge, a mathematical link between two identical, mirrored versions of spacetime. The idea was to maintain coherence between Einstein's general relativity and emerging quantum ideas, not to open pathways for space travel. Years later, other scientists associated this bridge with the famous wormholes, but this connection strayed far from the original intention. Recent research, including the work of my team, revisits this concept and shows that the Einstein-Rosen bridge may mean something much deeper than a hypothetical tunnel through space. The real enigma that Einstein and Rosen were trying to solve was how quantum fields behave in curved spacetime. From this perspective, the bridge acts as a mirror on the very structure of spacetime. It connects two microscopic arrows of time, one pointing forward and the other backward. Quantum mechanics governs the world of tiny particles, while general relativity explains gravity and the structure of spacetime. Uniting these two theories remains one of the greatest challenges in physics. Our new interpretation may pave the way for this union.
Decades after the work of Einstein and Rosen, the popular idea of wormholes as passages that could be traversed emerged. Studies from the 1980s showed, however, that this is impossible within general relativity. The bridge closes so quickly that not even light could pass through it. These structures are unstable, unobservable, and exist only as mathematical constructs, not as real portals. Even so, the wormhole metaphor has spread throughout popular culture, inspiring films, books, and many speculative theories about black holes connecting distant regions of the cosmos or functioning as time machines. To this day, however, there is no observational evidence of macroscopic wormholes, nor strong theoretical reasons to expect their existence in Einstein's theory without adding exotic and unproven physics, such as matter with negative energy. Our recent approach rescues the Einstein-Rosen bridge with a modern quantum view of time. The fundamental laws of physics do not differentiate between past and future or left and right. If we reverse time or space in the equations, everything continues to function. Taking these symmetries seriously, the bridge ceases to be a space tunnel and comes to represent two complementary parts of a quantum state. In one, time advances normally; in the other, it rewinds, like a reflection in a mirror. This symmetry is not just a philosophical idea. At the microscopic level, quantum evolution needs to be complete and reversible, even in the presence of gravity. The bridge arises because, to describe a physical system in its entirety, we need to consider both directions of time. In everyday life, we ignore the reverse and choose only one of the arrows of time. But near black holes or in expanding and contracting universes, both directions become necessary for a consistent quantum description, and that is exactly where Einstein-Rosen bridges naturally appear.
At the microscopic level, this bridge allows information to cross what we call the event horizon, the point of no return of a black hole. Information doesn't disappear, it continues to evolve, but follows the opposite, mirrored temporal direction. This idea naturally resolves the famous black hole information paradox, proposed by Stephen Hawking in 1974. He showed that black holes emit radiation and can evaporate completely, seemingly destroying all the information that fell into them, something that contradicts the quantum principle that information is never lost. The paradox only exists if we insist on using a single arrow of time to infinity, something that quantum mechanics does not require. By including both directions, information does not disappear, it simply abandons our temporal direction and reappears in the reverse direction, preserving everything without the need for new and exotic physics. These ideas are difficult to imagine because we are macroscopic beings and experience only one direction of time. In our daily lives, disorder, entropy, always increases. A broken glass doesn't mend itself, this creates our arrow of time, but, in the quantum world, things can be more subtle. Interestingly, there are already indications of this hidden structure. The cosmic microwave background radiation, the echo of the Big Bang, exhibits a small persistent asymmetry, a preference for one spatial orientation instead of its mirror image. This anomaly has intrigued cosmologists for 2 decades and has a very low probability in standard models unless we include mirrored quantum components.
This view leads to an even deeper possibility. What we call the Big Bang may not have been the absolute beginning of the universe, but a quantum leap between two phases of cosmic evolution with inverted times. In this scenario, black holes would act as bridges not only between directions of time, but between different cosmological epochs. Our universe may be the interior of a black hole formed in a previous cosmos, a closed region that collapsed, underwent a quantum leap, and began to expand, giving rise to the universe we know. If this is correct, future observations may confirm the idea. Relics of the pre-leap phase such as small black holes could survive the transition and appear in our expanding universe. Some of the invisible matter we attribute to dark matter may be composed precisely of these remnants. From this perspective, the Big Bang is not an origin, but a passage from a previous contraction. We don't need space wormholes. The bridge is temporal, and the Big Bang becomes a portal, not an absolute beginning. This reinterpretation of Einstein-Rosen bridges offers no shortcuts between galaxies, time travel, or science fiction portals. It offers something much deeper, a consistent quantum view of gravity, in which spacetime balances opposing directions of time, and our universe may have a history prior to the Big Bang. It doesn't invalidate Einstein's relativity or quantum physics, it merely complements them. The next great revolution in physics may not lead us to travel faster than light, but it could reveal that, at a microscopic level and in a bouncy universe, time flows in both directions.